Yeah, thanks for joining today of the Julia User Group Munich with a Julia session on graphs. Today's topic is Graphs.jl. And yeah, before that, just a little reminder again, because we have a mixed group always. So just a couple of months ago, I started my own Julia company. Now it's renamed to Julien.io. It was previously Julia Performance, but because of trademark reasons, I had to rename. Still, renaming is through, so I'm very happy to continue here. And if you have any ideas where to set Julia in your company or kind of academia, just use cases you have in mind, please drop me a line. I'm always curious. Okay, so first thing in this very notebook is to initialize some seeds because we have some randomness in it, and just to have it make the same thing every time the notebook is executed, we initialize a seed. The Graphs library describes itself as the project. The project goal of Graphs.jl is to mirror the functionality of robust network and graph analysis libraries such as NetworkX. So NetworkX, you may have heard, this is the library from Python, and it does a very good job at being feature rich. It does not such a very good job at being performant and speed, but yeah, the Python spirit, you have the functionality, and yeah, and almost everything there is going to be replicated in Graphs.jl. There are still some things which are not replicated, but the feature set is really, really huge. Okay, so I have split it into two notebooks. The first is just for the very basics, so that you understand what this library is actually about, and so this the basic graph structure. And I have then a second notebook where I just mention how to compute with the graphs. So the first one is the larger one, but still, let's see how much time we have. Okay, so yeah, first thing to clarify, which they also do in their GitHub page, the Graphs.jl package defines the central graph structure. So what you get here is really kind of the data structure, like an array, yeah, but now the optimized one to work with graphs. And there are two versions of it. The undirected graphs, it's called just graph, and the directed graphs called digraph. And they really emphasize this, and I think this is also very important. So what Graphs.jl does not is that it stores additional information on top of this graph structure. Like you have persons being the nodes of the graph here, and then relationships being the edges. So additional information to the persons, they wouldn't be stored in this graph itself, but in additional storages outside from the graph. So the graph data structure is really optimized for performance, and this is the main reason why these extra stuff is taken outside of it. But we will see also in this notebook a way to add this extra information, so it's thought of and also included, but just not in the very basic graph structure. Okay, to get everything running, I have two packages here. The first, the graphs package, and then a graph plot package. And the graph plot package is one of the possibilities how you can plot graphs. And it just turns out to be the most convenient. It does what you want in most cases. Isn't in your way and has intuitive namings, but there are actually alternatives to it. But because of the ease, I also chose this one. So let's construct a graph to get you in. So this is the constructor, and we have a first argument, which is the number of vertices, and the second argument, which is the number of edges. So if we execute this, we get also a representation with curly braces, which just summarizes this. This is because it gets into the type. So Julia uses curly braces to indicate types. And this is what we also see here. Okay, then we have two functions to manipulate such a graph and to set it up in a very dynamic way. So the add vertices and the add edges. So we can, for example, here add 2 new vertices, and now you see the representation changed. So we have now a graph which now has 3 nodes. We could do the same again. Yeah, we can execute the same line again, and now you see we have 5. No, we don't want that. And yeah, so here be careful on this add vertices. You can't execute this twice and expect it to behave just as if you would have it called once. So this is really not idempotent. But to the opposite, if you add an edge, there's only an on or off switch. So we now added 2 edges between the node 1 and node 3, and between node 1 and node 2, sorry, and node 3. And this you can re-execute and nothing will change. So it just updates kind of this edge to, okay, here's an edge. And if you do this again, it stays the same. Okay, so if you would have added an edge which is not there, so like adding an edge to node 4, you here we have this error. And let's take a look. So I was expecting it to fail. No, it still works. I'm very surprised. So this edge is kind of ignored here. So it's always good to know the special cases. So if you add an edge to this 4, it's going to be ignored. Let's rerun it. Yeah, I've rerun all these lines. And as you see, we add 2 edges, but finally only 1 is added. So it looks like it's silently ignored, but this is part of the interface. You won't get an error. What you get is a return value. So this is important to know for these cases. And it is a common interface for all in the graph library for all functions, which behave similarly. So no real error, no warning, but you can kind of catch the return value and see, okay, this edge adding didn't work out. Okay, so let's add our normal edges again. Okay, so then we already saw the gplot function. This is our plotting function. We put our graph in, and we can add some extra stuff. There's also documentation around it. So this is really the graph plot package, which provides the gplot function. So I added the node labels so that we can see, okay, this is correct. We have our node 1 connected to 2 and to 3, being the middle. This is not needed. Okay, so what I want to show you now is understanding how simple this whole thing is. So we now set up a graph, and we can inspect the internals of the graph. So there's the field names function, which gets in a type. So we get the type of G1, and we see that there are 2 attributes, 2 fields to the graph. And the one is the number of edges, which is 2. And the other is an adjacency list, where we have for each node, so each line corresponds to the node, the corresponding neighbors, which are then connected by edges. And this is really it. This is everything to the graph type. So with this very simple information, everything else is built up on top. And it's also nice to see that this is really just basic Julia stuff. So you could have invented it yourself if you want. Yeah. Of course, you need to write these algorithms in an efficient way, but nevertheless, the very basic is super simple. So if you want, this is already a performance improvement, yeah, because you could have also inferred the number of edges from the adjacency list itself. But there's an extra value to it probably for performance. Okay, so you shouldn't use these directly, but I think it's really good to see that this is a super simple data structure. But nevertheless, these dot axes in Julia are usually not the interface itself, but the interface is always defined via functions. So you have a couple of functions. I'm just listing some. So you have, for example, the neighbors. Yeah, if you have a graph and we want to get our neighbors, you can do this flexibly with the neighbors function, and we get this. And you see it's really corresponding directly to the line. So this is O of 1. Yeah, we just index our adjacency list and get our neighbors out. So this is super quick operation. We have also common neighbors operation, 2 and 3. Yeah, so you can imagine it's very similarly simple. Yeah, we index into our adjacency list and just intersect the two. So still a lot of speed. There's a standard degree function, which just shows how many edges there are, which are connected to one, or which, yeah. There's also a version which is directed, and then you have the respective in degree and out degree. But we will see a graph later on. Then there's also the number of edges and the number of vertices, which have these shortcuts so that you can easily use them. So if we would do a G-plot, which is a bit more flexible and only depends on the graph, not hard coding the number of nodes which we have, we can do it like this. And we can also name the edges respectively. So this is very nice. Okay, so basic stuffs, and then there's kind of a couple of more. So we have vertex iterator and edges iterator, and they just a short interruption. Ari, can I ask you to turn off your video? That would be nice, because we are recording, and it's just easier for everyone, especially for me, if I need to cut the recording, if the video's out. And that's also important for those who joined, so session is recorded, but you can raise your voice anytime you have questions, and yeah, and get in. You can also use the chat. So these vertices and edges, they are optimal iterators. So they iterate over all the vertices and they iterate over all the edges. So I have this special splashing syntax so that I can make them into a vector. This is why I use this little surrounding here. But then you can see that the vertices are really just simple numbers. And the edges, they are wrapped into a special type, which is called the simple edge. But then within it, it's just a pair. So it's, yeah, very simple structures. But here, keep in mind, they are iterators. They are no plain lists. Then we have a couple of extra support. We have an incidence matrix, which shows us the connectivity. So we have each, this is relatively directly the adjacency list we had above. So remember, the one was connected to 2 and 3, and then the others are only connected to 1. And this is the very same graph, just as a sparse matrix with 0 and 1. We have also the famous adjacency matrix, where it's just showing each node against each node which is connected. And there's the Laplacian matrix, which is also readily available. So a little bit more complex. You have a -1 everywhere where there was a one before, and on the diagonal, you have the degrees of the nodes. So simple stuff. You can do a lot of things with this. And yeah, and I put you here the documentation about the graphs. Okay, so now I would like to give this to you. And I'm sorry that today the compilation is not done in time. So the binder is still compiling and hasn't returned. So I'm going to switch this. Yeah, we need to cope with that. So nevertheless, yeah. So I will fill in this now on the fly. So the starting point is our G1, and let's plot this again. And the little task is now that we would like to make this a triangle. And always easier to have the node label, number of vertices. And so the solution here is really just to add another edge. And the way you do it is use the add edge function. And then you always need to add the graph you want to manipulate first. And then we have some noise. Thanks for joining. Let me see whether I can turn off the noise. I can. Okay, perfect. Okay, so I'm adding the edge between 2 and 3 and can plot this then just afterwards again. So I use a gplot. And yes, I get the triangle. So that's a very, very simple one. Okay, so I would like to go on. So we have kind of other ways to create graphs. One is to directly use the adjacency matrix. So we saw this before, and we can use this as the one and only argument, and it will realize that this is an adjacency matrix and construct it accordingly. This is a nice thing. So we have now two triangles, and we can compare them, and they're indeed comparing to true. So that's also a nice feature. You can kind of compare whole graph structures. Of course, in more complex graphs, you have some symmetry so that the precise numbering might differ between graphs which you can actually map on top of each other by symmetry. So then they won't be true. But in this simple case, the indices are actually also aligned. So this works. Okay, so finally for this construction, there's also destruction. We have a remove vertex function, so this can really be dynamically changed. But yeah, one important remark here is that it will reindex everything. So the graph underlying data structure is really meant to is really optimized for performance, and there's no node left 0 or something or undefined. So you could implement this by making this whole line undefined, but keep everything else. But this is not the case. It's going to switch the very last node to this node, so that so that the graph will re-index everything. So you see it now that this is 1 and 2, and we just deleted the 1. So it could have been 2 and 3 in other definitions, but this is not the case. And this is also why you really should use a specific package if you want to add metadata to this thing. So like if you have persons as nodes and you want to add person information, then it's not a good idea to implement it yourself. Like, use the indice and then store some extra information on it. This is not wise. There's a specific package to it. We will come to it. That's the metagraph, and this is the thing you should use then. So this is a word of caution for this part. Okay. So then I have a little section that you can create random graphs. So there are many, many ways to create graphs. This is one of the big features of the graphs package. I guess for many graph packages, you can use the constructor itself to generate graphs. So I'm using the very same like we did above, and I initialize it to 4 nodes and 3 edges. And this one is actually randomly assigning a couple of edges. So you see we have now 3. If I re-execute this again, I have 4 edges, and I can do this a couple of times. There's also a digraph constructor. We haven't looked into this, so this is the directed version. Everything is kind of completely the same, just that you have to keep in mind that the edges are now kind of directed. Before, if you have an edge between 1 and 2, it's the same as having an edge between 2 and 1. The direction, the order didn't matter. But if you use directed graphs, they do. So there are twice as many edges if you want. For each edge in a normal undirected graph, you have now 2 edges here, and they are distinguished accordingly. Okay, so there's another fancy thing here. It's a small graph function which has some cute internals. So you can plot a house, you can plot a lot of other things, and yeah, just a bit of fun. Yeah, and that would be my little second task for you. And I leave this now open. I hope that Binder is somewhere and ready. I can't promise. It looks like bad, but we'll see. Okay, so but there's a lot of more small graphs which you can use, and yeah, just have a bit of fun. So there are other functions, and if you need a specific graph, take a look at the so-called generators. So we have here now constructed the complete directed graph, so that everything has here the directions in both directions, and we have a click. We have a click of 3 nodes each and 4 clicks. So you see here the clicks which are then connected, and there are many more such generators. You can take a look there. They are listed. Okay, so that was the very first super basic part. And now I would like to show you that you can actually kind of, not compute, but you can combine these graphs together. So there's one super awesome part, which is the Cartesian product. So let me shortly get you through this code. I'm constructing a regular graph, plotting it. I construct a tree graph, plotting it. And then what I do is to construct the product, the Cartesian product of the two, and plot it. And it looks like this. So a bit large. So we have the regular graph, which is just a triangle again in our case. And we have the tree graph. And yeah, you see the tree if you think about this node being the top node. So we have a binary tree which always splits in two and splits in two and splits in two. And now if we use the Cartesian product, we have this nice structure where you see that for every node, we now just have a triangle. Or you can also kind of take it the other way around. For every node in the triangle, we now have the tree. So this is symmetric, and that's really nice. You can kind of construct easily very powerful graphs with this. Yeah, so we have another one. This is kind of the opposite to it. What we saw was the product, and you can kind of regard this as a sum. This is called a block diagonal, and it just takes two graphs and combines them in one by sticking them together. So these are kind of, as I think, the two most basic operations, combining graphs, sum and product. And yeah, and as you know, if you multiply and sum numbers, you can do quite a lot with this. So you can also do quite a lot with just these two basic operations. It needs a bit creativity or background knowledge with graphs, but these are very powerful operators already. So here's a little exercise to combine the two operators and just create things twice in a sense. But yeah, so there are other operators. There's also a full list. One fancy operator is the tensor product. Can be quite tough to get the mind of. So tensor product is it's a little bit like a Cartesian product, but a bit more mathematical. So it's another way of writing the product. And there was actually a random picture, so a graph layout, which was visualizing it very well. It seems like it was by chance that I've seen this. Yeah, okay. So I advise you to also understand the tensor product. There's a nice Wikipedia page on it. Yeah, and there, here on the top right, there's a lovely little picture on how you can imagine this. So you have one graph which is just linearized. So like usually you have the vertices indices. So node 1, node 2, node 3, node 4, node 5, and the same for the other one. And then you construct the pairs and only put an edge where there's an edge in both graphs. And yeah, this sounds restrictive, but it's actually not. You see that we, in this little setup, we added a lot of edges in the tensor product. Yeah, and yeah, and there are mathematical properties to this which you can use, and it's also just there, and yeah, makes also for some nice graphs. What's important also maybe that you can also construct a complement, so you can really use plus minus algebraic intuition. They work a little bit different here and there on graphs, but still you can really adapt the same operators into graphs. So this path graph, you remember this is just line, and the complement of the line looks like this. Okay, so there are a lot of more helpful functions. And yeah, you have also a function for a subgraph. There's an egonet, which is also similar for a subgraph, but there are many, many more how you can combine informations from two graphs. And this induced subgraph is also very specific. We'll see it later down, how you can then just pick out a certain subset of your graph, like a filter. Okay, so this was the basic graph support. Yeah, I hope we'll come back to this. So this graph algebra is very powerful and you can play a lot with that. So in the real world, you also have input-output issues. So you can save your graphs and just construct a random one. So there are many of these functions. Yeah, this is just another method how to construct a random graph. And this is now using the method of Erdős-Rényi. Wrong. So you can always inspect further documentation first time now in this session by adding a question mark in front. And yeah, and you see kind of further information on this algorithm. So this is yeah, very feature complete, the ways of generating graphs. So we can save it by just calling the save graph option. And the standard extension is the LG and Z for compressed. LG stands for light graph. And light graph was the name before. We now use Graphs.jl, but it's just very recently, like half a year ago, that this renaming happened. Before that, someone else blocked the name, and now it was opened, it was freed again, so that this graph package, which is really the standard graph package in Julia, get the general name. But this is sometimes you see it, or actually quite often you see it in some documentation, that people still use LightGraph. It's also still available, so these will work, but this is really just the same. So LightGraph, let's name it LightGraph.jl, is really the same as Graphs.jl. Okay. So we can load this again with the load graph function and have the same graph, but now G-plotted differently because the layout is always computed on the fly. And we can also take a look at what is actually stored in this file. Even though it's compressed, we have a direct representation in this case. And we see that there's the number of nodes, the number of edges, some extra information about the types in it, and the edges itself. So it's a very simple format. Yeah, and there are other formats for graphs which are already out there, and you can support them. You can use them with the Graph.io package. And very important, if you want to get started with this, For different formats, you need different other extra packages. It's not that easily documented. So yeah, if you use this to import, please remind this line. So if you have some dot or GML, then you need the parser combinator package. If you have some LG compressed graph format, you need codex alib, and yeah, the fourth for the last example. Yeah, and they just need to be installed in the system to work. But the error message you get if you haven't installed this extra package is not very much self-explaining. So yeah, it's good to know this pitfall. But then we can actually just read the normal format. So I have here GML format, which I write to a file, my graph.gml. Yeah, this is a completely different representation, as you see a bit more text in it. But you can also load this, and the way you load this now is also a little pitfall. Therefore, I definitely want to show this to you. The last argument you always need to change depending on your format. So here's a GML format. It comes from the Graph.io package. And then you also need to change the second argument. And yeah, and it also is a bit, yeah, not so self-explaining if you see the error on the first time. So if we load it, we can load it and we see that's actually a really simple graph. But if we leave this out, it will actually default to graph and we get an error graph not found. So it will always, this package, this graph format can store multiple graphs into one. And this is why that uses the second argument, which defaults to graph. So it could be a bit more intelligent in the sense, yeah, if it sees, oh, okay, this format, despite being able to represent multiple graphs at once, it actually only has one graph, so we pick that one graph. This is not the case. Yeah, so instead you really need to know the default name. And this is a directed graph, a dgraph. And yeah, and this is because here in this line we have a directed one. So in this case, it's especially hidden if you haven't worked with these formats before. So good to know to have this argument here. Yeah, so another little example is dot format. You may have seen this beforehand because you can kind of make some nice graph visualizations with dot. So we have a simple directed graph. And here's a similar node. So it's always helpful if you name the graphs as explicitly. So I had a lot of problems with reading in graphs which don't have this name, and the name is always here after the graph directive. And then if you have named it, you use the name here in the name field. And remember to change the format, and then we also get this in. So there, as said, in the other formats supported too. If you encounter some problems, yeah, they are fixable. So the package itself is very stable, and it might just be kind of one peculiarity with your graph structure which you have. Just getting a bit back, you see that the GML graph can add a lot of extra stuff, and it might be that one of these extra stuffs is not supported as of now from the parser. So this might be one thing, or yeah, the naming thing. But anyway, so there's a test set in the Graph.io package. So you really can just take a look at what they do as standards, and you see for each graph file format that they have the test cases which successfully run, and so you can just pick the example from there. Okay, so I'm going to, yeah, I think this is the second big part of the first notebook. So the graphs, as said, cannot store extra attributes, and we have a little extra package for that, and it fits in this introductory setup. But just before that, um, do you have some more questions? So I think this is now a good point to just ask questions to the basic graph. If there are no questions, no problem. We will see a couple of more features here and there, and it's actually a very simple data structure. Everyone knows this. Okay, so feel welcome as always to ask questions in the chat also. The Metagraphs package is now the opposite of the very performant core graph data structure. With the Metagraphs package, we can add extra data to our graphs, which we use for certain use cases, like I said, a network of persons or a network of computers, or like a representation of a map in a network where we have a lot of extra information. So there's, again, we construct kind of a random graph. Here we use the regular graph again. So this is a circle, and we construct the metagraph by piping in the graph itself. And this is the default weight, because one of the general use cases of attributes is, for example, to have weights, so that the distance between the distance of an edge between two nodes is not always the same. You can change this by now changing the weight property. By default, everything has a weight 1, so this makes things simpler, but you can change the default value now by changing this little value here. The metagraph otherwise is completely the same as the normal graph, and you can use all the functions. So we have here the number of values. Yeah, we can use gplot, and there's no difference. All functions are supported on Metagraphs too. So what does Metagraphs do in addition is that they have a little key value store wrapped into the graph, and there are some functions to access this key value store. So we can set some stuff, we can get attributes, we can also remove things, and we can check if a property is existent or not. So this is really basic stuff, and it's meant that basic, but it gives you kind of all the skills you need just to combine some extra information to the nodes. So let's take this example. Yeah, we have the set prop function. First argument is always the graph itself on what we operate. Then here's the property. So we use this colon syntax, which creates a symbol. Actually, this, yeah, sorry, that was, so you see the symbol does nothing. But if we use the type of to get the type, we see that this is a symbol. And this would be a string. And yeah, sometimes the one is a bit more efficient than the other. And for the usage as a key, we usually in Julia always the symbol is used. It's a bit more performant. And on this key description, we just store a little value. So you see that we can also add stuff to the graph itself. Yeah, this is now a generic property. And you also see the same pattern again as before. So this function actually returns a Boolean value indicating whether this worked or not. And yeah, most of the time it works, especially if you do it in script-like fashion. Yeah, and you can now set props also on specific nodes. So the syntax is super identical, but now we add an extra integer as a second argument. And we can also add the integer if we call for the props. So we now set the name to John, yeah, and we see also that it changed. So it was also returning true in this regard. Yeah, so there's an S version of it. Of course, we can also add several at once. Then we use a dictionary. So same here. And yeah, we can also do this twice. So this set props is not overwriting everything, yeah, but just adding it. It's very intuitive actually then in this regard. So if you would like to delete everything or overwrite everything, you clean before and then you overwrite. So if you want to have edges, you can also add stuff there. So this is either supported by the edge version, and because this is undirected, I just wanted to show you this. There's really support of not confusing these two. So I'm now using the edge in the other direction, and it really gives me also the information I just added. So this is because we have an undirected metagraph. And we can also use just that without the edges and add another integer as another argument to it. And it works also for the props. So this might be a bit more intuitive if you write it a lot. Yeah, so with this basic feature, you have the support that all the properties are correctly taken over. If you delete a vertex, vertices, a node, or an edge, then everything is kind of correctly handled. So this is the management the metagraph does for you, and it's really recommended to use this if you have such extra information, because doing it yourself will just not work good as soon as you destroy a single node. Of course, in very special cases you can do it, but yeah, this is the reason why this package exists. And despite you have really simple stuff, yeah, it's very useful because it knows the graph structure under the hood. Okay, there's some further functions which might be handy for you. So if you have this meta information, you can of course use it. And one application is to filter on this information. So you can filter on concrete values, but you can also filter on just what actually has this property or what not. So this is now the place where also the induced subgraph function comes. So it's very intuitive. Yeah, we have a graph which we put in, and we have some vertices now here coming as an iterator with which we want to construct our subgraphs. And this is then what the induced subgraph function does, that it takes all the edges from the original and yeah, removes all the edges which are coming outside so that we have a proper graph. And that returns our subgraph together with a map from the old to the new vertices. Because as you know, for performance reasons, we don't keep old places for nodes. We don't keep old integers, but we reorder everything so that they start from 1. So you see this is a tuple, and we just get the tuple printed. So we have now a graph which really only has 2 nodes and 1 edge between them. So this was preserved. And our mapping here is really the identity mapping. So it just turned out now in our case that our node 1 is mapped to the previous node 1, and our node 2 is mapped to the previous node 2. And yeah, and we can also now use our props feature, yeah, and get our edge here, and we see that all our extra information was really preserved. So this was the edge, despite it's now kind of in a different graph structure, it's still there. We can also do the same with edges. And in this case, yeah, we have the edge still there, so the subgraph will also include it. Okay, so the last part of the metagraph version is that it can also be used for weights. So as we already have seen, there's the default weights. Okay, yeah. And yeah, and we can also change this via another function, but we can change it by the constructor. And let's keep in mind our graph. Let's plot it again here so that we can see it. So that was the circle. And let's also plot the node labels. Vertices. So yeah, we have the 1, 2, 3, 4, 5. So yeah, it's a random graph. So and what I now want to look is the shortest path from 1 to 5. This is why I want to print this. So we can use the yeah, I don't know how to pronounce that, the extra shortest path algorithm, and you need to split it into 2 parts. So the first one is where you start the search. Yeah, we started from node 1, our graph, and it will construct an intermediate representation, which you then ask to look for shortest paths to another node. This is for performance reasons, so that you can reuse this intermediate storage. The enumerate paths function is the second one now, where you can add the second, so the destination. We have here the target node and here the destination node. but still you can now store this intermediate variable and reuse the computation here. So the first one goes over 4 as expected. And my little example here is adding a weight to the wrong side. So we need to change this. So let's add the weight from 1 to 4, this edge, make this very large. So that worked. And now we see that the shortest path changed. Just a little, very little demonstration that this works. And you can use these weights now for the shortest path functions. So this is used quite a lot, so much actually that there are far more use cases where you want to add weights but no other properties, and then you can get some performance boosts again. And this is why there's a very special package, simple weighted graphs, which support this use case that you have a normal graph with the weights on top. So yeah, in this case, take a look at that package and use the graph there. And yeah, things will just be a bit faster. So that's the underlying reason is that this is stored as a dictionary. Yeah, and the dictionary changes, they take just more time as if you would store the weights more efficiently in an array. And this is what is done in the simple weighted graphs. Okay, so I've some bad news, unfortunately. So the binder compilation didn't work out. I will update the meetup notes and the discourse note as soon as I get the binder working, so that you have the notebook at least afterwards, so you can experiment with this. I'm sorry for the inconveniences. So the last part for this introductory notebook is that I want to point out that there is actually an alternative to the Graphs package, which can give you also very good performance, and especially if you consider to add these metadata. So as you see, just by having the simple weighted graphs, there is a performance penalty if you add these extra properties to it. And yeah, and depending on your use case, and yeah, with Julia, you sometimes really want to have the optimal performance. And there's another way you can approach these graphs computations. And one is CATLab. So you use category theory to represent data structures. And it was just last year at JuliaCon where there was a talk about AC sets, which is attributed C sets in the long form. And they have really nice properties. So they're somewhat between data frames and graphs. So an alternative way to describe is that they are like a database in memory. So like a relational database in memory. So you can have multiple tables which are linked by foreign keys, and this all represented in one unified data structure. This is very handy and also so far implemented with special Julia features. Maybe you've already used them, not sure, it's an advanced feature. There's Julia's generated functions. And with this, you can create code on the fly so that you have optimal code even for special cases. And this is what the Graphs.jl has done. So if you have the case that you have a specific graph structure with certain properties, which are not just represented by simple weighted graph, but you would need a metagraph, and yeah, unfortunately you are hit by performance, then this is really a good place to go. Just documentation is still an issue. So yeah, it's not that easy going like the Graphs.jl, but I still want to mention it. And this is one benchmark slide I took out of the YouTube video I linked here also. So this just compares with not the best resolution, but we can make the most out of it. So this compares the CATLab with light graphs. As already said, this was the previous name of the package. So it's now just the graphs library. And sure, they also have some performance improvements in there. But back then, and not so far back yet, July last year, the SCADLab implementation, despite not being optimized for graphs, but for this general relational databases and memory stuff, they compare quite well with the light graphs or with the graphs implementation. So what is depicted here is just the time of some operations, and the cat labs are normalized to 1. And yeah, so smaller bars are better. And in this case here, the light graph, so the first is the has edge operation. So if you call the graph and ask it whether it has a certain edge, then yeah, it needs to search through the graph efficiently. And the implementation in light graphs is apparently faster. Yeah, but for a second, this is the iterator for the edges, which you use actually quite a lot. There, the generated code from the CATLAB implementation is a factor of 2 faster or worse to that point. And this is kind of how you can interpret these graphs. So they compared a couple of operations on graphs, and yeah, baseline. Summary is that they are very good in performance. So there are some performance like the connected components of symmetric graphs where you have a factor of 2 here, even a bit more here. So there are some edge cases where it's not that good yet, but it could be a really good replacement. And this is comparing it to the graphs library. And not taking into account that the CATLAB now can create the same efficient code also with custom attributes, with custom properties. So as soon as you add some extra properties to your graph where you want to not only store the weights, but maybe some extra information, then the system is exactly as efficient, but can handle also this extra information in the same efficient way. So that's just nice to know. And I will probably do another introduction session on the CATLAB part to give this a little bit more ground. Okay, so that is that. Okay, that was the first part. Are there some further questions to these introductions? So you've seen the underlying graph structure, a very simple data structure optimized for performance. You've seen how you can create it, how to manipulate it. And yeah, you've also now seen kind of on the supplement side that there's an extra package, the Metagraph package, to organize your extra informations, your attributes to it. This distinction is really mainly done because of performance reasons. And finally here, in case you need kind of both worlds and also performance on the attributes, then there's one alternative to it, not so good documented as of now, but a valuable alternative if you really face the performance problems. And this is then the CATLAB. Okay, nice. Then I'm going to switch to my little second notebook and show you. Let me see, is it the same Zoom? Yeah, it's the same Zoom. And so show you kind of one concrete case how you can apply this graph package. So again, I'm using some random seed. So apparently I have something still running in the background, but doesn't matter. So what we use is the very same package. I'm just using another standard plots package for some histograms. As an introduction, so we remember that the graphs package was not only for performance, but it also strives towards being feature rich and feature complete, just a robust network and graph analysis library compared such as Network X, like Network X would be for the Python ecosystem. So there are a lot of functions actually on top of this basic structure, which are more in the algorithm part, and which are there if you need them. And I want to start this notebook section with one concrete example. So I took this out of an example notebook given by the Julia Graphs, the Julia Graphs organization on GitHub. And this is about a simulation. Let's imagine you have your network of friends and you post a new image or a video, and you want to understand kind of how much influence you actually have on the network. So yeah, this is even more important if you kind of really want to change some opinions. So yeah, usually the idea is that you best need to be an influencer, and the post you send needs to reach like 1 million at once. Yeah. And there was called Mr. Watts, who built a Watts model simulation, a very simple one. Hence, we can look this up here now. We can re-implement it, which shows that actually it's not important to be such an influencer with a super degree, with super many friends. But for something to go viral, to cascade in the global network, it's sufficient to just have a few friends, so to say. So it's a really nice little application. So let's look into the code. It's very simple. So we have these 3 functions, just that you have an understanding. We are not going to go through much, but this is just enough. So we have one function, which is just a little helper. This computes in our network of persons, yeah, just the fraction, how many of our other neighbors are already engaged, I say it here, so which are already posting it, reposting the post, yeah. And this fraction is just computed by going to the neighbors. So thanks to Julia, we can now really use these very basic functions and don't need to worry so much about performance, because these iterators, they are already performant. So I always like this part of Julia. In Python, you better look for a special function. Yeah. So if you want to sum up over all the neighbors, yeah, you better look whether there's a function sum up over all the neighbors. And in Julia, there's no need for it because everything already is optimized for performance. You don't need a special function which wraps some C++ code, but you can just use Julia. So we use a standard for loop to go through our neighbors. We check whether our neighbor is already engaged. There's, from the code I copied here, a little optimization. You could just use a dictionary or a standard vector, but here they they save some bytes and use a bit vector where you have really just one bit for representing 0 or 1. And this is also the reason why we have this comparison to true. So normally you would have an if engagement, yeah, but because this is a 0 or 1, we need to compare it to true. So because in Julia, you may not have seen this. This is actually working, yeah. So you can compare Boolean values to integer values, or to number values in the sense. So Boolean is a number. Okay, so this is used here to have some performance, and then we just add up 1 to our engaged neighbors. So this is actually super efficient code, yeah. And in Python, this would be super inefficient. Okay, yeah, and finally we take the we divide it by the number of our total neighbors, yeah. So just to have the fraction. So very simple function, yeah. And it shows like one of the most important parts, that you really can use these basic blocks and build efficient graph algorithms on top of it. Okay, so then we have an update engagement function. And what does it do here? So before we used the neighbors function. Here now we just use the vertices function. But let me shortly summarize what the output. So I've wrote here in the summary, it updates the node status of all vertices, one iteration only. So this is missing adaptation from me. I wanted to make it a bit more friendly. So that was the previous name they used. So what it does, it updates the engagement of all vertices, but just doing it once. So yeah, and how does it does it? How does it do it? We get the graph, we get the current engagement, and we get the threshold. So what we do, we go through all our, let's say, persons, yeah, our nodes, vertices here. We do this in a random order. We shuffle this iterator, and yeah, and then if we are not yet engaged, we may get engaged. And when do we do this? We do this if our peer group is kind of enough engaged. Yeah, so we look at our fraction, the function we just had from where we are, and if this fraction is large enough, so there's a threshold parameter, then we ourselves are engaged as well. So this is the very simple algorithm here. And we do this once for every person in our graph. So we really kind of do this iteratively one time through. So if you change things on the first persons, yeah, these changes will affect already later persons in this loop. Yeah, but finally, this is just one loop through all persons. Okay, there's a return nothing. Yeah, doesn't matter so much. It's just kind of changing the graph. Okay. Let me see. Sorry, I'm just trying again the binder part because it's a little bit annoying that it's so unstable currently. I would love to send you kind of the working binder session at the end. So let's take a look in the last function. So we've seen now just two little functions which use super basic functions of our nodes. Yeah, so we have used the neighbors and we have used kind of all the vertices. And now we implement the actual simulation. So the simulation of this spreading event just does the above updates a couple of times. So we get number of persons, the number of nodes in the graph, the special graph. Actually, we're going to see that. We get the what's called the average degree. Here it's named Z. I copied this now from the part. I hope this is intuitive enough. So this is the number of friends you have, so to say. Yeah. And yeah, what we want to show is that we don't need so many friends, yeah, to actually make a spreading event. Then we have the threshold. So which portion of your friends need to be engaged so that you also get engaged. We have the timestamps, so that the number of times we run the above update step so that you get engaged if your friends are engaged. And we do this a couple of times. So this is for the statistics. We repeat the entire process a couple of times to see some statistics on it. So it's really basic stuff. This may look kind of a little bit extraordinary, but yeah, you see this quite a lot if you use vectors. If you want to pre-allocate a vector for performance reasons, this is the way you do it. You specify the type of your vector, and then you have an undefined special function, which is there in Julia base. And then you specify how many elements you want to have the vector. Yeah. So this is what we're going to return. And yeah, and then there's a special value which we put into our random graph generalization, in a random graph generator, sorry. So then comes the big loop. So this is our statistics loop. We just repeat the same process again and again to get some statistics out of it. And what we do every time is we generate a random graph according to this Watts-Strogatz algorithm. We're going to take a look actually how this looks like. It's always easiest to have an image. But it just has this parameters, and from the paper where this refers to, they initialized the other parameter to this apparently. We start with kind of no engagement, but a single person is already engaged. Yeah, so it really starts spreading from a single event, from a single person, the entire system. And then for t times, we update our engagements again and again and again. So each iteration goes through all persons. And then finally, we sum up how many persons are actually engaged. So this is super efficient now. And we store the output in our pre-allocated vector and return it finally. So this is very simple stuff. I haven't executed the other functions, so let me this as well. Okay, so I hope you could follow this one. It's just a couple of very simple functions, but it's kind of also something you could use again. So random graph generation to simulate something and get some statistic out of it. You can also do this with other random graph generators. Here there's the Strogas generator. But you can use the same idea, of course, with other generators. And this is maybe, I haven't said this. So this is really just picking one random vertices which we initialize. So actually not really much graph here. So the one graph idea is really the random graph generator, which is used here. The other thing is just a simple plain Julia. Okay, so let's initialize our parameters. So we use just 1,000 persons in our networks, and we say that each person has about 5 friends on average. So random graph changes here and there. And we say that if kind of just, let's say 1/5 of our friends is engaged, then we also get engaged. So, which is actually a pretty interesting detail. So as soon as one of our friends is engaged, we also get engaged. And then we repeat this for 50 time steps. We upload our graphs 50 times, and we do this for statistics. For just we repeat it 100 times. And what I want to show you first takes a bit more time. Is how this graph looks like. I think I do it afterwards. Let's first look into the histograms. So this is kind of a nice little extra. I want to show you just if you haven't seen this in Julia. Remember, I wrote my function with the semicolon in front, and this makes all these parameters be key value parameters. And this is especially handy for such top-level function, which just have a lot of parameters. And we can use the same semicolon on the other side so that these are actually not passed out by position, but passed by name. So this is, for me, I always find this very handy so that I don't fear, okay, I don't know the precise location any longer. And if I do it this way on the very top level function, I'm sure that I can't mix them. I just use the right names and then it works. We've called the simulation apparently, and then we've just plot the data in an histogram. This is relatively fast. And what the original paper then does is just to increase the number of friends by 1, the average number of friends. So instead of 5, you have now 6 friends. So what does it mean? Like we have a threshold of engagement of 0.18. So it means that like 2 of your friends need to be engaged. Yeah. So this is, I think, the big difference now. Because the threshold is just set this way, now 2 of your friends need to be engaged that you also get engaged. And if you plot this again, the plot. Oh, now I executed the wrong part. let's see. So now I executed the plotting itself. Do I interrupt? Yeah, I interrupted. Okay. So the second simulation now with just one average more friend shows a completely different setup. So as feared, my interruption does not work, but it's okay. It's the usual thing. And it also doesn't take so long. Yeah. So what I wanted to show you is just how to imagine these graphs, but we could have done it afterwards. Now it seems like we get the plot first. Just make a quick check to the running notebook. Okay. Now it should have returned both. Okay, so I got this interruption signal now completely. And there's the result of the second one. And it looks completely different because of the range. So it's really just above, we have kind of number of engaged nouns goes to up to 2000. And here we have it up to 2. So we see that there's kind of no event happening at all, which kind of spreads to the whole system. And in the simple case here of just 5 friends, and you get engaged when just one friend of yours is also engaged, you already have a very pronounced cascade effect. So this is a nice simulation. Let's kind of let's try to rerun the simulation over here, because so this picture is a little bit easier to compare because there was now just one little one little sample at the other side. And yeah, so you see it's really just at almost, there's almost no cascade at all. Yeah, this is a nice effect you can simulate very easily with just a simple graph tools. And yeah, and if you, as soon as you get this binder ready, I hope it's going to be better the next days. You can also play with these parameters. So one of the things, of course, to change the threshold now, for example, to make it also for the 5 persons, above 0.2, so that you need 2 friends. And if we simulate it again, we should see kind of also, a similar part that, okay, it's hard to get 2 friends being engaged at once. So also this breaks down. But it's still a very powerful effect, so that if you have only a few friends, it's likely that your friends also only have a few friends. And then, you just don't need so many friends which are engaged so that you yourself get engaged. And this effect is what is simulated here. And this can be quite powerful. So that if you have just the networks of small friendships, circles, you can get a huge cascade effect. Okay, so I now want to finally also give you an image of what this networks look like. I hope this will plot in a second. And maybe just one last note for this key value syntax here, because I've already used it here, just haven't named it. So you see that I now use the key value syntax just in the middle of nowhere, and the Z is now pointing to my Z2, and this just works because there's a shortcut. So this is actually kind of like this. We just don't need to write it. So I like the syntax very much. It gives you a clean overview if you have such high level function with a lot of parameters, and you can also change parts of it. So for this example, it's ideal. Works very well, very clean parameter handling. Okay, so nice. So I hope this turn of view is going to be there in the future. This was almost it. So what I now summarized for you is here just that there are a lot of ready algorithms. So with this example we just went through, and we're going to see the graph a few seconds. Let's use just very simple functions, but you can also use just these plain simple functions and get a really cool simulation, network simulation. But sometimes you just need a bit more, So we have algorithms for path traversal. if you have, probably the famous graph coloring, so that with 4 colors you can color every graph so that no two colors are neighbors of each other's. And yeah, and you can do this with coloring algorithms. You can compute distances, centrality measures. You can inspect the graph whether there are some internal structures which are interesting. So they're called community structures. You can also try to decompose the graph into smaller things. And yep, so these are all core stuff. I will just give you a short look into it. So these are just links to standard documentation, and you have a lot of functions in here. So breadth first search, depth first search, and some search algorithms and the path stuff, connectedness. So there's really a lot of features. You see my scrolling on the right. So there's a lot of functions in here. So whenever you need a precise function, chances are high that's already there. We have the coloring, yeah, so that you can do this special problem of coloring a graph. We have distance measures of the graph, centrality measures. So yeah, probably if you haven't used them, yeah, there you may not know the terms, but yeah, do a little search if you go into the graphs. So there's a lot of research on these graphs, and it's nice to have the implemented algorithms here. Community structures might be a bit more intuitive on the naive guess. Yeah, you have clusters which you can identify, and graph decomposition. Yeah, okay, so there's a lot of stuff. This is what I wanted to point out. There are some extra packages. So matching graphs, there are some algorithms, something which is called network interdiction. I haven't looked into it. It's part of the light graphs extra. It gives you kind of some extra graphs itself, but also this network interdiction part. Yeah, just take a look there and if you need it. And also an extra package for partitioning, which is not Julia code actually, but so-called Metis library, but has an interface to the Graphs library. So you can use this special partitioning software on graphs also with the Graphs.jl. Okay, to have a little better overview of what is in there, there's actually a subset of all these functionalities which also work in a parallel setting. So yeah, these are also documented in the documentation, but I think it's a good simple overview. So if you can't decide which algorithm you want to choose, these parallel algorithms are probably very well, because in case you need the performance, you then just can take a couple of more computers or cores and speed things up. It's always a big advantage, and can be actually also a crucial advantage. So not to use the most state-of-the-art algorithm, but to use one which scales. Okay, so finally, there are also some other prepared notebooks from the Graph community, which prepared kind of a similar case like the one I showed you today above, where you have the spreading event simulation. So there are some other simulations which are also just great to follow.